Hi, in this video we want to take a look at a method to pre-process our data before we do our model building. Okay, so think about the process of going through and building predictive models. So my first step is going to be designing data collection, data prep. This is where we're at right now. Then we're going to build our models. We're going to evaluate our models, and then we're going to make we're going to select the model. Then we're going to make our predictions. And think of it as this way: the earlier in the process it is, the more important it is. All right, so if you make a mistake early on, it's going to go through, and that mistake is going to propagate all the way through. So maybe not mistake's not the right word, maybe a poor choice, maybe something happened beyond your control. Well, anything that is less than optimal is going to propagate all the way through. And my view of machine learning is that the way to learn machine learning is to go at the at the output at the end, start at predictions, then do model selection, then do model evaluation and model building. I feel like the right way is to go in reverse. That way it's easier to understand why this is important. So this is data prep. Data prep is pretty early. This is a critical feature. And I feel like a lot of times students don't fully, like if you try to do data prep before you do model building, a lot of times students don't really understand why this is important. This is fundamental. This can make or break your project very consistently. All right, so for this data prep, we're going to look at what I feel is like the simplest version. What we want to do, we want to go through our predictor variables, and we want to change their average, or their standard deviation, or their minimum, or their maximum. Why do we do this? Okay, so by standardizing these univariate statistics of our variables, this makes it, first of all, easier to understand or easier to interpret the importance of a variable when we go through and we're trying to do feature engineering, when we're trying to go through and select which variables are important. If I have different variables on different scales, on different standard deviations, like very, very different ones, sometimes it can be hard to tell which one's important, which one's not. It can be hard for the human to figure it out, and it can be hard for the machine learning algorithm when we're doing the model building. So by standardizing, it makes it easier to spot. So I usually do this, honestly, when I'm doing my model exploration phase, where I'm just exploring different models. I'm exploring which variables are important, and I use this information to make choices on what will be used in my final models. I personally don't do this a lot. Well, I mean, it depends on the data, honestly. Data mining and predictive analytics is a bunch of subjective decisions. I usually like to use, if possible, the original data, but sometimes if the scales are really thrown off, I'll go ahead and use this in the final one. But that's for me personally. I prefer this for variable like exploration, then select the variables but use the unchanged ones on this. My personal preference. The other reason why we do this is some models just won't even, or some implementations of algorithms will not accept values outside of certain ranges. So sometimes you'll be doing like a neural network, and the system wants all of the predictor variables to be between 0 and 1, or -1 and 1. Those are very common. And if I don't have them, from 0 to 1, or I don't have them from -1 to 1, depending on the implementation that I'm working with, I'm going to get a crap model. So I need to be able to do this. All right, so let's go ahead and look at the first version. The first version is what statisticians usually refer to as normalizing. All right, so normalizing, what we're doing is we're going to go through our predictor variable. We're going to subtract off the average. So now every single entry, or now after I subtract off the average, that predictor variable now has an average of 0. Okay, and then what we're going to do after we subtract off the average, we divide by the standard deviation. What does that do? Well, that dividing by the standard deviation sets it up so that the new transformed version has a standard deviation of 1. So the predictor variable has average 0 and standard deviation of 1, and it's going to be constant throughout. I do this a lot. This is the one that I prefer the most. That's because I have a stronger statistics background than I have in computer science. My experience is a lot of times the computer scientists, those who are doing more with neural networks than with like spreadsheet problems like I work on more often, they tend to prefer going from 0 to 1 or -1 to 1. It's up to you, whatever works best for you. Okay, so let's go ahead and go through an example. All right, so for this data set, or for this example, I'm literally copying and pasting from scikit-learn. And up here, let's go ahead and clear this. All of that was me just writing the code to make sure it ran before I started filming. Good thing to do. So let's go over here and let's go. It doesn't print for me, but here is the website. If you want to take a look, there's a lot of good stuff. This is the first part of the pre-processing part of the web page, and this is a good place to start. Oh, and whenever you hear unit means 1 in mathematics. Or, well, if you're doing abstract algebra, unit has a more complicated meaning, but when we're dealing with numbers, unit means 1. When I multiply, I get the same value back. But there's, if you start doing abstract algebra or possibly number theory, unit can also mean other elements. Okay, so let's get scikit-learn. I specifically want pre-processing. And then let's go ahead and get NumPy in. Now let's go ahead and pull in or generate our training data. So we can see here are our entries on our training data. Now what I want to do, I want to center and scale my training data. Let's take a look at our scaled version. All right, so check this out. What we did, and I'm going to go ahead and just show you kind of like the output real quick. All right, so here's the original average. So if I look through here, this adds up, this column adds up to 3. If I subtract off, or sorry, they add up to 3. If I divide by the number of observations, 3 divided by 3 is 1. So this has average 1. Here these add the -1, the 0, and the 1 add up to 0. The average is 0. Here, these 3 values of 2, 0, -1 add up to 1. Divide by 3, I get 1/3. Okay, so in the scaled version, what happened in the scaled version, it went through, it took the average, it subtracted the average from the entire column, subtracted 0 from the entire column, subtracted 1/3 from the entire column. Then it went through and divided by a standard deviation, standard deviation, standard deviation. And so now in the transformed version, if I was to go through each of these columns and compute the average, I would get 0, 0, 0. Okay, so now what about the standard deviation? Well, the standard deviation originally, in the original training data, we have 0.8, 0.8, 0.12. Okay, well, these standard deviations are not far off from each other, and so really it's not necessary if I was doing a machine learning on this scale. But if I was to have something like standard deviation of 0.2, and another one is a standard deviation of 10,000, those are 2 very different scales, and those can throw off some of my models, specifically clustering. Okay, so what we do, when we rescale, we get a new standard deviation. So if I was to go through and compute the standard deviation of these three values of this column of the new data set, I would get standard deviation of 1. If I go through and compute the standard deviation of negative 1.20 and 1.2, I would get standard deviation of 1. And then here, if I go through and compute the standard deviation of 0.13, negative 0.2, and negative 0.11, I would get a standard deviation of 1. All right. So here, this is a better version of the data for certain model building. And also, if I was to go through and start doing let's say I'm doing logistic regression, or I'm doing regression, Poisson regression, generalized linear models. As I go through and I look at the statistical significance of my predictor variables, well, what I'll notice is that closer, it's not 100% true, but the standard standard error on the coefficients are going to be closer to constant values. Well, what that does for me, that means that the coefficient and the t-value of the hypothesis test are going to be proportional to each other. They're going to be pretty close. So it's, when I look at the coefficients, it's easier to interpret that is statistically significant, and makes it easier for me to spot what's important. I don't need to think about p-values. I don't need to think about I don't need to think about the the t-value. I don't need to think about the number of observations for a particular level of a categorical variable. I still need to think about that one, but it's not as important. All right, so now as I went through and I was building my model, what's going to happen down the road? All right, so I built my model and I'm really excited. I get my new data. New data comes in, and I need to make a prediction on my new data. So let's say I'm trying to predict Christmas sales. All right, so it's January, February, March, something like that. I've got last year's Christmas data, and I want to predict Christmas sales for next year. Or more specifically, I want to build a model so that I will be able to predict Christmas sales in a few months, so that I can tell my boss, hey, we need to build a lot of this particular toy because it's going to be the hot toy. Or we want to put our toys in these stores, not in these stores, and make as much money as possible. All right, so what I need to do, so I subtracted the mean and I divided by the standard deviation. So when I get my new data set, what I need to do, I need to subtract off the mean from the training data. So I take the new data that I need to make the prediction on, I grab the average from my training data, and I do my subtractions. And I take the standard deviations from my training data, and I divide on that test data. All right, so to be able to do that, what we're going to do, I'm going to use this pre-processing. Oops, I hit caps locks by accident. I want to do pre-processing, standard scalar, and I'm fitting on my training data. So this is going to be a new function, and I'm going to apply this to my training data when I get it, or my scoring data. So really, I should be saying scoring instead of test. So when I get my new data in the future, and on my test set also, when I get the data that I need to make the prediction on, I'm going to use this function to actually do it. I'm actually not interested in this code here. This really isn't that important to me. I'm just using this as an example to help you understand, or hopefully, if I'm successful as a teacher. If I am, let me know. If I'm not, if I'm sucking, let me know. All right, so here, scalar is now a function where the average of the training data columns is what I'm going to be subtracting off, and the standard deviation from this of the training data is what I use to make my divisions. All right, well, let's go ahead. What is that average? What is the standard deviation? All right, well, it's the same values we saw a moment ago, 1, 0, and 1/3. And then for the standard deviation, it's exactly the same ones we see. All right, so some way, some shape, some form, I have to store these values and apply them later. The standard scalar function makes this as easy as possible. It's beautiful. It's beautiful. All right, so now if I was to go through and I apply it to the training data, I can see that this is how it's going to transform exactly the values I got. I don't want to do it previously. I did it manually so that hopefully helps you understand, but I want to use the standard scalar function. Really, that is the way to do it. That's the smart way to go. All right, so now let's say I've made this predictive model, and I'm hanging out. Life is good. I'm working in data, and my boss runs in and says, "You need to make a prediction with these predictive variable values." Okay, so for this situation, I've got -1, 1, and 0 as my predictor values. So of the three variables, I need to make a prediction. Now, I remember that I pre-process my data beforehand. So you always want to keep this in your code to remember it, so it just does automatically. But so what I do, I go ahead and I grab that standard scalar transform that I already built of, that I called scalar a moment ago, and I apply it to the values I need to predict. So here, if I take the average from my training data, so let me clear this and maybe make this a little bit easier. X train. All right, so if I take the average here and subtract it off this -1, then divide by the standard deviation on this value, I'm going to get -2.4. If I take the average here, subtract it from this 1, and then divide by the standard deviation here, I'm going to get 1.2. If I take the average here of 2, 0, -1, so 1/3, if I subtract that from here, then I divide by the standard deviation of these three values, then I'm going to get -2.3. All right, so what we're doing, when I make my predictions, I'm replacing -1 with -2.4. I'm replacing 1 with 1.2, and the 0 gets replaced by -0.3. And so this way, I'm doing everything on the same scale as the training data that I use to build my model. This is probably the most important when you're working with neural networks. All right, so in that situation, what we're doing, we're rescaling the data so that we have an average of 0 and a standard deviation of 1. And I feel that this is the most useful, most important when I'm doing regression. And I feel like that's where you get the most bang for your buck. Also, this is a good choice to do for clustering models. Anytime you're doing something that is going to have like statistics, if you're doing statistical analysis, scaling with mean 0, standard deviation 1 is probably the way you should be leaning. Remember, regression really is more of a statistics thing, less of a predictive modeling thing. When I get into things like neural networks and some of the more exotic model building structures, this is less important. All right, the next one we want to talk about is where I want to change the minimum and maximum instead. So previously I was interested in getting the average and standard deviation to be where I want it. Now I want to change it so that the minimum and maximum values are within a certain range. And now times that I would want to do this is, so it, first of all, it puts everything on the same scale. So if I had, one predictor variable goes from 0.1 to 0.9, another one goes from 0 to 10 million for different variable range, then those are very different ranges, and sometimes models can have problems handling it. It could be it'll also, like, dealing with bigger numbers could be an issue just within the computations of the system. And it can make it harder to interpret what's important when I do variable exploration and feature engineering. Okay, so we're going to go through something very similar. My goal here is to set it up so that the minimum value is within a certain range. So I'm going to say that the minimum value is 0 and the maximum value is 1. All right, so here is my training data. Once again, now what I'm going to do, remember, I want to use that pre-processing operations in scikit-learn instead of doing it manually. I want to use the functions that are already built for me, because people have, if I build a function manually and I'm reinventing the wheel, I'm the only person who uses it. So if there's a bug, there's very little opportunity for it to be found. If I'm using the functions that have already been built by other programmers, all of them have been using it over and over and over, bugs are going to get found a lot better than custom functions that I build. Now, you're working in data science, you're going to have to build custom functions, but if you don't need to reinvent the wheel, don't. Use what other people are doing if it suits your purpose. So I'm going to take the pre-processing min-max scalar. All right, so this function, what it's going to do, it's going to set it up so the minimum and maximum go from the minimum is 0, the maximum is 1 for all of the different values. So let's do this thing. All right, so now, min-max scalar is a function that if I drop in a value to be fitted on, or sorry, a data set to be fitted on, it's going to go through and it's going to find the algebraic or the linear equation. Yeah, it's still algebraic. The linear equation to transform future observations into the 0, 1 range on this particular scale. All right, so here is the X train min max is the transformed data after I go through and fit it. Okay, so let's do this. Take a look at what we get. All right, so let's look through. In each column, my goal this time is to have minimum 0, maximum 1. Minimum 0, maximum 1. All right, that's good. And 0.5 is in between. That's good. Any value between 0 and 1 is acceptable. All right, minimum value of 0. Now I've got maximum value of 1 and 0.5 in the middle. That's fine. I really don't care about the 0.5 right now. All right, minimum value of 0 and maximum value of 1. If I go through and I look at where's the minimum value in this column, it's at the bottom. Where's the 0? At the bottom. Maximum value is in the middle on this column. Maximum value, the 1 is in the middle. Minimum value is -1 up top. Maximum value is 1 at the bottom. I should see 0 at top, 1 at the bottom. 0 at the top, 1 at the bottom. This is going good. Now, maximum at the top, minimum at the bottom, I see that I've got, and when I say minimum and maximum, a negative value is always less than a maximum one. So we're not considering the magnitude of the numbers. We're considering its position on the number line. And I see exactly the top is 1 and the minimum is the bottom. All right, this is good. All right, so down the road, I'm hanging out. I've built my models. New data comes in and I need to make predictions so that I can be the star data person in my organization, because I want to give actionable insights. So what's going to happen is I have new values coming in. I need to train, before I put those new values into the model that I built, I need to transform it into the same minimum maximum range as I did on the training data when I built it. All right, so let's do this thing. What I'm going to do, my new values are -3, -1, and 4. All right, so now let's go ahead and transform it using the min-max scalar transform that I just built a moment ago. All right, now there's something important to see in this. previously on my training data, I had minimum 0, maximum 1. What do I see here? I've got a negative 1.5. That's less. Hey, you're like, hey, Aaron, that's less than 0. Well, check this out. What was my minimum value in the original training data? The minimum was 0. Now, the minimum is negative 3. This value is less than any other value that was in the predictive, or that was in the training data. So it's going below negative 1. Okay, so now the next one, I see that I've got negative 1, right? That's equal to the minimum value I had in the training data. So I should get a 0. Do I get a 0? Yes, I do. All right, that's good. Now I see that I've got a 1.7. 1.7, that's greater than 1. Why is that? Well, 4 is greater than any value in the training data on this column. All right, so depending on the implementation of how things are working out, how like the neural network is algorithm is built, this might be a problem. I might want to replace this negative 1.5 with a 0. Basically, that would be calling out that it's less than or equal to 0. Any value greater than 1, I replace with 1. Possibly something I might want to consider, because potentially, depending on how like the weights are working, this might start pulling things farther down than I really want them to. Now this 1.7, since it's greater than 1, this could make it so that if this ends up being like an outlier, this could have a large impact. Now this is more of a data prep material, which is a different course, super important course. When you get there, be excited. It's hard to understand why it's important, but your data prep is critical. All right, so now let's go ahead and think about something that, how is it like from a linear equation point of view, how is this actually being executed? Well, what's going to go through, and down here is the actual equation, how this works out when we do the standard deviation. This is my equation to put things on the 0-1 scale. What we're going to do, you'll notice that the first thing we do is we subtract the minimum. After we subtract the minimum, we divide by the range, the maximum minus the minimum. That is the linear equation for doing this transform. So the first thing I need to know is, if I'm looking back at it and I want to see what's going on, I want to know what is the minimum. Well, it's 0, 1/2, and then 1/3. And then what is the difference between the maximum and minimum ranges? And here we go. Okay, so now one thing you need to realize about this is that if you look at the documentation, we went through and we used a transformed version of the data. That's important. All right, so you can see that the ranges are kind of a little bit different than what you would have expected looking at the original value. All right, so and here's how you transform back and forth. Here, so if you need to go in reverse. Yeah, sometimes after you build your model, so you transform it, you put it in your model, you make your predictions, and like when you're looking at your transformed version of your data, you want to convert back, but you don't remember how you did it. This is the equation to do it. That's the inverse function from your college algebra. All right, the next one we want to look at is transforming, instead of from 0 to 1, -1 to 1. Now, let's take a look. So here is our training data. Once again, all right, now here I'm going to do maximum absolute scalar. So previously, we looked at, let me scroll up a little bit. There we go. We went min max scalar. Now we're doing max absolute scalar. Okay, so let's go through. Let's take a look. All right, now I've got my function to do transformations. I need to fit it on my training data. Now let's take a look at what do we get back. All right, so here we can see that the 0, 1 values, the absolute values correspond to the magnitude of the numbers. So what this did, this went through and this did the 0, 1 transformation on the absolute values. After it did that, it went through and it converted negative values to -1, positive values that were originally negative, or values that were originally negative are now negative, and values that were originally positive are positive. Okay, so what this does is that the minimum absolute value gets transformed to 0, and the maximum absolute value gets transformed to 1. So this is a little bit different. Before, it wasn't considering absolute value at all. And this is a good way to go. Now, when do we want to do this? When the position on the number line is not as important for this. You really just want to kind of explore your algorithm before you make a choice on which one to use between these two. Both are probably going to be good choices. You need to double check, like, what is the algorithm expecting to get? And I would be doing this more for machine learning and not really for statistics. Just like with the other time that we're transforming from 0 to 1 and we're transforming from -1 to 1, I'm really not going to do that when I'm interested in something like hypothesis testing. All right, so if I transform, so let's say that my new data that I need to make a prediction on is -3, -1, 4. All right, notice that -3 is less than the minimum value here. 4 is greater than the maximum value, and -1 is equal to the minimum value, and it's equal in absolute value to the maximum value. That so the absolute value maximum is equal to the -1 absolute value. So let's take a look. So when I do this, I see that I get -1.5. All right, so since this is less than, so it's greater in magnitude than all of the values, I got an absolute value greater than 1. And since it's negative, it got a negative sign slapped onto it. All right, here, this is equal in magnitude to the maximum absolute value here. So it became a 1 in magnitude. And because it was originally negative, it became a negative value. Here, this 4 is greater in magnitude than any of these values. So I know before I even look, I'm not looking at it. I know that it's going to give me a value that's greater than 1 in absolute value. And since it's positive, it's going to be a positive value. Well, let's look down here. And so this is 2. That's greater than 1. All right. So something I would want to consider, depending on my model, I might want to replace this -1.5 with a -1 and this 2 with a 1. This would be especially true if I felt like I had some outliers going on. If I had some really extreme values in my predictions, or my values I need to predict on, then I might want to consider kind of like muting it down to get it down to -1 to 1 range. Something to consider. There's other ways that I could, like, if I had, like, I did transform so that the training data goes from -1 to 1, and then when I transform my data that I need to make a prediction on, I end up getting something like 10, something like way bigger. Then I probably don't want to put 10 in the model, because that's so extreme that it's probably going to give me an extreme prediction that realistically is not going to be correct. So maybe a 2, maybe a 3, something like that. I personally, will usually transform it down to a 1 or -1, and I need to remember that when I see a 1, it's equal to the maximum absolute value. All right, and so here is the scale. All right, and the documentation, if you look at the website where I copied and pasted this stuff from, I can see, it starts talking about scaling sparse data. One issue you always have to consider is that you may, specifically when I do my range values, if I have very little data, or I don't have, if I have a lot of missing values, it might be that the maximum value in my training data is not a good indication of the maximum value in the population of what I'll see later down the road. It might be that the minimum value in my training data is not a good representation of the minimum value I'm going to see down the road. So we have to be ready for that. Basically, this talks about this aspect. Also, there's issues with collinearity when I do stuff like this. Doing this type of transformation, I can lose information, or I like if I have, let's say, 3 or more predictors that are highly correlated with each other. And when I say correlated, I'm using that in a more linear algebra, a greater sense than we usually talk about in machine learning. If I have something like close to linear dependence among a group of predictor variables, that feature can be lost by doing this rescaling. And that's true for all 3 versions that we talked about. So you want to take a look at it. At this point in the sequence of courses that you're talking about, you really don't, it's not something to worry about. But when you get to your data prep course, this is something that will be important. You need to think about this. Now, scaling with outliers, if you have like an outlier, let's say that there was an error in your data and you see that, all of your values go from -3 to 3, and then you see a 20 besides, all the other data. That 20 probably is wrong. So before you start doing this, you want to deal with your outliers first. Because that can throw it off. So remember, I was talking about means and standard deviations, right? Originally, well, if I have, the mean and standard deviations can be thrown off by like one outlier. Also, if I have an extremely large, like error or outlier in the data, or extremely small, small minimum value, that can also throw off these range calculations. So before I do this, I need to be more mindful of it. This is one of the reasons why I use this personally more for variable exploration than I do for actual the models themselves. And usually, if I go through this, I'll find like an outlier that I missed in my first go through as I'm looking at my data. All right, that's all I've got. I hope you're staying healthy. I hope you're enjoying the class. Take care and have fun.